Hello, thank you so much for tuning in today to learn about more about flow rates at changing conditions. All right, so our problem involves ammonia, NH3, and it's initially flowing at 303 liters per hour at standard conditions, and these conditions are changing. The temperature is increased to 150 degrees Celsius, and the pressure is decreased to 608 millimeters of Hg, and we want to know if the mass flow rate is increasing or decreasing, and by how much in the units of grams per hour. Okay, so what are we doing? We're going from STP, standard temperature and pressure, to not standard temperature and pressure. So what do we have to do? Well, overall what we want is we want to look at the mass flow rate initially and the mass flow rate final, and then we want to compare these two. Okay, so first let's start by getting the initial mass flow rate, which we know how to do at standard conditions because we did that in the previous video. So let's write what we have: 303 liters of NH3 per hour, and we know at STP we can use the conversion, 22.4 liters per 1 mole of NH3, and then we can go from molar flow rate to mass flow rate. With the molar mass, for every 1 mole there are 17 grams of NH3. Okay, and at this point we have our correct units, grams per hour, and then what do we get? Multiplying this out, we get 230 grams of NH3 per hour. Okay, so that is our initial mass flow rate. All right, but what about the second part? We want to get our mass flow rate at conditions that are different from what we started with. All right, so what we have to do is combine our PV equals nRT equation. We have to combine two of those equations, one for the standard conditions and one for not at standard conditions. So the way we do that is we write each equation separately. This is at non-standard conditions, and then at standard conditions we have this. Alright, so how are we going to combine these? We're going to divide the first equation by the second equation, and then what do we get? Okay, so you can see that the r's would cancel out, and we get this new equation here, which I've written out on a separate piece of paper, and we want to isolate the molar flow rate so we can eventually get the mass flow rate. So what does that become? N dot equals P V dot over PS V hat S times TS over T. Okay, and we will plug in our appropriate values. So remember, the subscript S just means at standard conditions, so PS is 1 ATM, VS is the 22.4 liters per mole, and the TS is 273 Kelvin. But to introduce our new conditions, our new pressure, and our new temperature, they also have to be in these same units. So the pressure that we were given of 608 millimeters Hg, that equals 0.8 ATM, because there is 1 atmosphere for every 760 millimeters of Hg, and when we convert it, this is what we get. And then temperature of 150 degrees Celsius. That just becomes 423 Kelvin. And we have to use these values so we can cancel out our units. All right, so finally crunching the numbers. What do we get when we plug in these values? We have 0.8 ATM times 303 liters per hour over 1 ATM times 22.4 liters per mole multiplied by our standard temperature over our new temperature. Okay, and you can see a lot of these units cancel out, and then we're just left with moles per hour, and that is moles per hour like this because they're both in the denominator. It gets flipped, and to get that into our mass flow rate of grams per hour, we need one last conversion, and that's going to be that there are 17 grams of NH3 for every 1 mole, and then doing the calculations, we get our final mass flow rate to be 119 grams of NH3 per hour. Okay, and now I think we can answer our question. So we went from 230 grams per hour to 119 grams per hour for the mass flow rate of NH3, and we can say that the mass flow rate for NH3 decreased, and they also want to know how much it decreased by, so it decreased by 111 grams per hour, and I think that is a good final statement. All right, as always, thanks for tuning in. See you again hopefully soon.